Good morning, everyone. We continue today with the sound. Today we'll cover the beats, intensity, and loudness of the sound. In last lecture, we talked about the acoustic resonance. We've seen the three types of resonators that creates this resonance, and we looked at how to calculate the harmonics for those structures, where basically we found that the frequency for the open or for closed structures is defined by n equals to v divided by 2l, where n takes an integer number. However, for the open closed structure, we saw that the fundamental is happening at lambda over 4, and the frequency is given by n v over 4l, where the n are the odd numbers. Just to refresh our memories with the resonance, we have this question where basically the question says, I have three aluminum rods with the same diameter. They all have different lengths. How does the fundamental resonant frequency depends on the length of the rod? So here we have three lengths, and we know that the frequency equals to V over lambda. So in this case, if the wavelength, which is basically related to the length of the rod here, we know that for the same rods, we have the same fundamental. For example, if we have here the rods are being open, then our fundamental is lambda over 2 frequency. Now, for the same types with the different lengths, this means the longer one will have a larger lambda. Here we know that the frequency is inverse proportional to the lambda, which means that the frequency for the one that has the largest lambda will result into the smallest frequency, which means if the rod length increases, this means resulting lambda will increase, which means that the frequency will decrease. So let's read here the answers. As length increases, the frequency increases. This is wrong because we know that the frequency and lambda are inverse proportional, and the lambda and the length are proportional, or L equals to n lambda over 2 for the open or closed, and assuming that those are from the same structure, and assuming that they're all open rods, the length is proportional to lambda, which means the frequency is inverse proportional to the length. So this is wrong. As length decreases, the frequency increases. This is correct. They all have the same fundamental frequency. This is wrong. These aren't musical instruments. Wrong. So the answer is B. Now we define a quantity called beats. The beats basically is interference of sound waves that have almost the same frequency, however, slightly shifted. The beat will be the result of the interference between those two frequencies that are slightly different. So if this is F1 and this is F2, then F1 does not equal F2. However, the difference is very small. So it's going to happen in this case if those two interferes due to the, again, construction and destruction, you will see that the result is going to be from that shape. The amplitude will start varying, and this is because of the destruction. Here, due to the construction, will be maximum. So if you want to look at the difference between the two frequencies, the result would be from that shape. Now let's look at those two examples. In those two examples here, we have two frequencies. The first one is 240 hertz, and the second one is a bit higher, 270 hertz. The beat frequency, the difference between both of them is 30 hertz. So this is the first case. The second case, I have 240 for the first and 300 for the second. So the beat here is less than the beat in this case. So the beat in the second case is 60 hertz. Here the beat is 30 hertz. So what is this beat? We've seen that the beat here is the resulting interference due to the construction and destruction. And as you can see, I'll start from this point where they are at the same phase, and then it ends here. This is for one cycle of the beat. At this point, where they completely overlap, beat number one is less than beat number two. Beat number two is higher in frequency, which means it's repeating more frequent than beat number one. This is the point where both are zeros. So that's the signal that we were talking about. Here they become at this point out of phase, or they cancel, and here they become in phase and also at the zero. The second one has a smaller period than the first one. Because the frequency in the second one is higher than the frequency of the first one. Now let's look at this example. In this example, we have an electronic tuning fork that is set at 440 hertz to tune a string of a guitar. A beat frequency of 4 hertz is hertz. The tuning fork has a 440 hertz. The beat frequency was 4 hertz. The string is tightened slightly, increasing the speed of the wave on the string, and a new beat frequency of 5 hertz is heard. So when we tighten the string, this means we have decreased the length of the string, and as a result, we will see that the frequency will increase. Now here, the new beat, so if this is beat 1, beat 2 is 5 hertz. If we look at this string, when this string was L1, then the beat was 4 hertz. Now when we tighten this string, this means we have made the string shorter, and this is because of the guitar string itself. Once you tighten it, you make it shorter. So I have L2 shorter than L1. Then the beat becomes 5 hertz. Now, in order to understand what happened here, we know that the beat is F2 minus F1 magnitude. So we want to know what happened if this is the, let's assume that this is my frequency of the tuning fork. Let's assume that this is F1 equals to 440 hertz. And then the beat was 4 hertz magnitude, which means either the frequency of the string is greater or the frequency of the string is smaller than the frequency of the tuning fork. However, when we tighten the string, the frequency, the beta frequency increased, which means the difference became larger than 4, became 5, which means that this F2 has moved up, right? Because the difference now increased. As this equals to F2 minus F1. So we have two options to have the B2 going to 5 hertz. Either F2 increased in the frequency or F2 decreased in the frequency. However, since tightening the guitar will result into a relatively shorter length, this means the frequency has increased. Why? Because we know that the frequency is inverse proportional of the wavelength. So decreasing the length will decrease the wavelength and will result into increasing the frequency. So F has increased, and this is the option, the only option that agrees with this conclusion. If 2 has increased, then the frequency F2 is greater than the frequency F1, and in this case, the frequency of the string at the initial state is F2 minus F1 equals to 4, where this one is 440, which means that F2 for the string at the initial case is 444 hertz. Now we will introduce the intensity and the loudness of the sound. A human audible frequency range goes from 25 hertz to 20 kilohertz. Above 20 kilohertz, most of a human being will not be able to hear the sound. Even some ears that go below 20 kilohertz. But in average, it is from between 25 hertz to 20 kilohertz. We introduce what's called the intensity, and this intensity is basically the sound power emitted or received per unit area. The symbol for the intensity is I, and it measures the amount of power received per unit area. The unit for I is watts per meter squared or joules per second per meter squared. So if the power is energy divided by time, which is E divided by T, then the intensity is power divided by area. Power divided by area is also energy divided by time divided by area. So this is the watts per meter squared. An example of asymmetric sound emission, which is basically a sound that transmitted in all directions, we call it also isotropic or symmetric sound emission. In this case, the energy or the power is generated at this point, and then this power is transmitted in all directions. So if this is the power that is generated here, then it makes sense if you go further away, and since this power is distributed and going in all directions, so it makes sense that this power that is generated here at the center will be divided by the area of the sphere. If we assume that that whale generated a power emitting in all directions, then this power, as I said, will be divided by that sphere, and that sphere will be including the point of interest. So here, for example, if I am standing here, then this power will be divided on all the area of the whole sphere. So in this case, I will take the distance between the source and myself as the radius for that sphere. And saying that, the I, the intensity, is the power P divided by the area of that sphere, where, as I said, R here is the radius of that sphere, which basically is between the point that where I am recording that power and the source of that power. The unit for this radius is meter. So according to the expression that I just derived, P divided by the area of the sphere, and we know that the area of the sphere is 4 pi r squared. This means this intensity is inverse proportional to the distance squared, which means the further you are, the less the power you receive, which means intensity will decrease with increasing the distance from the source. An example for the expression we just derived for the intensity. Example, vocalizations of an orca result in sound emissions of 120 watt per meter squared. So this is the intensity, 100 watt per meter squared at 1 meter. So I have I equals to P divided by 4 pi r squared, and then R is 1 meter, which means in this case, if I know R and I know the intensity, then I can calculate the power. Because as you can see, the intensity depends on the distance. Now the question is asking to find the measured intensity at 1.5 kilometer from the whale. If R is changing, then I will be changing as well. However, the generated power will be constant. So I can make use of the intensity given to me at this specific distance to calculate the power. The power is going to be the same for both cases. So here I can calculate the power, and I say the power is 120 times 4 pi, and R is 1, then the power is 480 pi watts. This power generated by this whale is not going to change. it's going to be the same. However, the intensity at those locations will be changing based on what? Based on this radius. Now I need to calculate the intensity at 1.5 kilometers. So let's assume that this is 1.5 kilometer, which is 1,500 meter. Definitely the intensity at this point will be different than the intensity at 1 meter. So let's calculate now the intensity here. The intensity here will be now for using the same power, however, the distance now is different. And in this case, I2 equals to P, the same power, 480 pi divided by 4 pi 1,500 squared. And in this case, I2 becomes 53.33 10 to the power minus 6 watts per meter squared.